All right, so we're going to look a little bit at some limits tonight, but they do connect to derivatives with a specific French guy's rule, which we're going to talk about in a little bit. But let's look at a couple of simple limits first, just to refresh your memory on limits. So let's find the limit of the first one. So what's the first thing you always want to try when you have a limit?
Substitution.
Right. Can we plug in 1 to this problem and get the answer? No. All right. So once we can't do that, what's the next thing we want to try?
Look at the graph. Graph it.
We could graph it, but there's algebraic ways to do it. Well, let's look at this first one. Let's look at the x squared minus x. Can I take something out of that? Yeah. So this becomes x and then x minus 1, right? And then we have, on the bottom, we have x squared minus 1, which can become x minus 1, x plus 1, right? So I can cancel those two out. And now I'm looking at the limit as x goes to 1 of x over x plus 1, which we now can do. And that's 1 half. Okay, so if you can't just plug in, start looking at ways that you can cancel stuff out. All right, and that works well when we're doing the ones to the any other number not necessarily infinity. The next one is going to infinity. So now we did the pre-calc method where you just look at the leading coefficients. I'm going to do the calculus method where we're actually dividing everything else by the thing, just because you're going to need to start understanding that going forward, especially when we're looking at sequences and series next semester in Calc 2. And if you're not going into Calc 2, it's always a helpful thing to know. So we're going to divide all these, basically everything, by the x squared. We're looking to get the denominators. We're looking to get those fractions, because the fraction, the denominator goes to 0, or goes to infinity, the fraction goes to 0. It eliminates things. So this now becomes 1 minus 1 over x squared, and then 2 plus 1 over x squared. So the 1 over x squareds go to 0, and this also comes out to be 1 half. So those work great. Simple limits. Obviously, if I'm doing this now, that's not what we're going to look at. So let's look at this limit. So we have ln of x over x minus 1. Can I just plug the 1 into it? No. All right, so can I factor anything?
No.
No. And if I plug in 1,
It's going to be denominator 0.
the denominator is 0. And what's the numerator?
Also 0?
Also 0. So I have 0 over 0. That is known as an indeterminate form. Same thing with infinity over infinity. Okay. So those are both known as indeterminate forms. So typically, if I had 5 over 5, that's 1. All right. Typically, if you have the same thing over the same thing, you're going to get 1. 0 over 0 doesn't come out to be 1. It's one of those weird ones. Same thing with infinity over infinity. It's not 1. So we needed to do something else to be able to find the limit in these situations. We could graph it. That is a possible way to do it. If we were to graph this one, let's look at it. Let's see what this one comes out to be. So we have ln of x over x minus 1, And we're looking at the limit as it goes to 1. So let's do x equals 1. So let's see where it is. So this kind of looks like it's going to go to 1.
1. Oh, on the line.
Well, yeah, because if I plug in 1, I'm not going to get it. So,
Going to 1.
right, but it definitely looks like it's going to 1. All right? But somehow we have to figure that out. We want an algebraic way to figure this out. We don't want to have to, because when we're looking at graphs, like this one kind of nice goes to 1, but if this was just shifted up just a little bit and it was going to like 1.23, like it's not something that we're going to be able to estimate very well or easily. So we want an algebraic way to be able to solve these, not have to necessarily do it numerically or with a graph. So this French guy, and I know it looks like L'Hospital, but it is not. Okay. It's L'Hopital. Just imagine he's from Massachusetts, where the way the towns are spelled are not how they're actually sounded. I went up to Salem this weekend, and we drove to the town of Peabody, and my girlfriend was sitting there going, "Wait, hold on, it spells Peabody." I'm like, "Nope, it's Peabody." It's Massachusetts' way of spelling things. So this is L'Hopital, and L'Hopital basically looked at this problem of an indeterminate form where we're trying to figure out, well, why does this work? How does this happen? So he said, if you take the limit of f of x and g of x, if they both go to 0, or they both go to infinity, either positive or negative, doesn't matter. We have an indeterminate form. Then, what he said was, if you take it equals the derivative of them. So actually, I'll do this, because this is the important piece. So if you have an indeterminate form, you take the derivative of f of x and the g of x. Notice this is not the derivative of the limit. Okay, so we're not doing the quotient rule. This is the derivative of the top and the derivative of the bottom. Take the derivative of those both. The limit goes to the same thing. Okay. If you want a proof of it, there's a proof in the book, and there's also a proof at the end. I'm not going to go into the proof. All right. So the key that we have to figure out now is, as long as we can take our limit and make it into a fraction where we have two functions, I can do his rule. If it doesn't work, if it's an indeterminate form, this rule now will make it something that I can actually work with. So let's go back. Do it afterwards. I did. Very good. And let's look at the same problem. So we've already determined this is an indeterminate form. So let's take the derivative of each. So my f of x is ln of x. So my f prime of x is 1 over x. My g of x is x minus 1. And my g prime of x is just 1. So the limit as x goes to 1 of ln of x over x minus 1 equals the limit as x goes to 1 of 1 over x over 1. Now if I plug in 1 to that, I get 1, which is what we showed on the graph that works. So L'Hopital's rule basically allows us to find the limits of functions that would fall into the indeterminate form.
What if it's still somehow indeterminate?
Do the derivative again. You literally can keep doing the derivative. As long as the function stays indeterminate, you can keep doing the derivative. Now, it has to stay indeterminate. So if the bottom is still divided by 0, but the top number came out to be anything other than a 0, it still doesn't work. That's not indeterminate. We'd have to do something else. So it's got to be 0 over 0, or infinity over infinity, or negative infinity over negative infinity. It's got to be one of the indeterminate forms. It cannot be something that works. And if it's still in that form, do the derivative again. Because the derivative would equal that piece, which goes all the way back. So you can keep doing the derivative until it works, as long as it stays in an indeterminate form.
So once you do the derivative, you plug whatever x selected back in.
Yep, see if it works. Or if that doesn't work and you can factor it at that point, you can factor it. Like at that point, you can do all your normal limit rules to try to find the answer to it. So, but if it's still plugging it in, still comes out to the indeterminate, you could always do the derivative again, make it simpler for you. So, those are the things you want to look at. All right. Literally the rest of the class is just looking at problems and trying to make sure Happy Tells rule works on it. All right, so we have e to the x over x squared. So if I plug an infinity to this, or if I divide it by the e to the x, it's still going to end up being, it's not going to work. So if I plug in infinity to this, the top's going to infinity, and the bottom's going to infinity. So this is indeterminate form. So let's do the derivative of it. So my f of x is e to the x. So my f prime of x is e to the x. My g of x is x squared. So g prime of x is 2x. Of e to the x over x squared now equals the limit as x goes to infinity of e to the x over 2x. If I look at infinity to this 2, what's it going to? Still infinity over infinity. So let's do the derivative again. So f second prime, we still have e to the x, and that goes to 2. So this now equals the limit as x goes to infinity of e to the x over 2, which goes to infinity. And it's fine. Like a limit can go to infinity. That is a valid solution for a limit. All right, this limit goes to infinity.
I just find it ironic that it's supposed to be indeterminate or infinity, but the answer is infinity.
Well, see, the indeterminate is different than that, though. The indeterminate is infinity over infinity. And whenever we're taking two things that are typically the same, when we're dividing, you would get 1. So that's why they're in indeterminate form, because they don't follow that rule. 0 over 0 and infinity over infinity don't follow the rule that when you divide them, they come out to be 1, which most people would like to do. So if we're looking at the beginning, it is an indeterminate form. At the end, it's not. It's infinity over 2, which is infinity. So it's no longer in indeterminate form, so it's actually a specific value at this point. Okay. But yeah, you can just literally keep going on your derivatives.
Give me an example where factoring is involved. Or is there?
Probably, but I have to come up with one that would work right? We'd have to do the derivative for it first, then figure out the factoring. Let's see if I can come up with one before the end of the class.
Okay.
Because that one actually takes a few steps of going backwards in my mind to come up with the one that would work. So, all right, let's look at this one. All right, so find me my derivatives of it. The derivative of 1 over x is, you have to change it to x to the negative 1. And then do the derivative of that. So it should be negative x to the negative 2 second power. All right, so if we're looking at the original problem, ln of x goes to infinity, the square root of x, the square root of infinity still goes to infinity. So we have an indeterminate form. We now have to do our derivatives for it. So I know that ln of x over the square root of x equals the limit as x goes to infinity of 1 over x divided by 1 over 2 square root of x. If I plug in infinity to the top and bottom of this one, I would get 0 over 0, correct? So it would still be an indeterminate form. Now, this might solve the question that you asked me before. It might not. Here's an example of where I don't want to do my derivative again. Okay? We have a function as of right now, and I might do my derivative, but I'm not going to do my derivative on what I have currently. Let's clean this up before we want to go do our derivative. All right? We have a fraction over a fraction. So if I look at 1 over x, and then we can flip this one over, so I have times 2 square root of x over 1, because keep change flip. I now have 2 square root of x over x, which equals 2 over the square root of x. And that goes to 0. So while it wasn't a factoring one, it was one where you don't want to just keep doing the derivative if you don't have to. All right, so once you've done it, this is where we were going back to that other thing before. It's like, where do you stop simplifying? You stop simplifying when you don't need to anymore. This is a situation where this is correct. It's not simplified enough to really help me. So if I do the simplification step next, I now have something that will work for me and help me.
Oh,
So
it's
you want
0 over 0, infinity over infinity, and negative infinity over infinity.
Over negative infinity, yeah. Those are the indeterminate. Like this one right here, this is 0 over 0. I plug it in. So that still would technically be an indeterminate that form. But I can simplify this it changes to 2 over the square root of x. And now it's no longer in the indeterminate form, that equals 0. So I now have my limit of that one without doing my derivative a second time. Okay. All right. Any questions with this one? Does that make sense?
Yes, you can just multiply by the reciprocal.
Yeah. Yep. Keep change flip. So. All right. Try this. So if you plug in 0 to tangent, you get 0 minus 0, 0 over 0. So this is 0 over 0, indeterminate form. So find me my derivative of those two.
The derivative of tan x secant squared x.
Yes.
Okay, so I would like nice.
Oh, I don't know.
So this one comes out to be secant squared x minus 1. So we're now at secant squared x minus 1 over 3x squared. If you plug in 0 to secant squared x, you get 1. So 1 minus 1 is 0 over 0. So it is still in the indeterminate form. So you have to do your derivative again, because there's no simplifying that.
Oh, I think it's also 0.
Yes, because tangent of x comes out to be 0. So this one still is 0 over 0. So, however, at this point, we can now do the derivative of the top and the bottom, but right now the derivative of the top is going to be a product rule, correct?
Yes.
Okay, so let's see if we can take that and simplify it a little bit. So this is where, when we start looking at it, it's like, okay, let's, I gotta go again. I really don't want to do it to that, so let's see what we can do to simplify this down a little bit.
Really quick.
Yeah.
Did you get the derivative of the top, so you bring down the 2?
So you have to do the chain rule.
Oh, you do the chain rule?
Yeah.
Yes.
So you're doing the, it's secant x squared.
Yeah.
So you're doing the derivative of secant x, which is secant tangent. And then the 2 comes down, and then it's 2 secant x, which that's where you can secant x squared. So yeah, you have to do the chain rule in there. I was anticipating somebody asking that question. No, you're fine. What? Oh.
I did like the trig identity, whatever.
Oh, you could have changed it.
Staggering identity.
Because what was it? That.
Sine squared. Cosine squared.
Oh, you did it that way?
One, and then I like divided it by cosine squared. And then
You definitely made your life harder.
Is the way to simplify it looking at the identity?
No.
Ah.
So remember, when we start looking at things, we can use the limit rules. And one of the limit rules states that I can break everything up and find the limits of every piece. So I can change this to 1/3 by pulling that straight out. That's the constant, right? 2 over 6 is 1/3. And then I can have the limit as x goes to 0 of secant squared x. And then the limit as x goes to 0 of tangent x over x. So let's break things up a little bit. So I plot my constant. And these are the things that, unfortunately, literally just come with practice. It's like, when you get to a point where you're stuck, it's like, okay, what else do I want to try? And this would have been messy to do with the product rule to really come out. So it's like, we have the limit rules, so let's use the limit rules. So I plot my constant 1/3, and I can break up my multiplication. Remember, since it's multiplied on top and divided, I can put that x at the bottom anywhere I want. So I pull out the secant x squared x, because I can find the limit of that. That limit is just 1 by plugging in, so that's going to be very nice. And really all I'm left with is that little limit right there. The tangent of x over x, which still is 0. So
The limit is 1/3, right? Because you can
Yeah.
square that, secant square x times the x.
yes, in a second it will be 0. It'll be 1/3. We're not. We have to do one more step to get there, though. All right. So this right there is 1/3. That right there is 1. That, however, is still an indeterminate form. So if I have f of x is tangent of x, f prime of x is secant squared x, g of x is x, g prime of x is 1. So now, if we did secant squared x over 1, that also is 1. So my limit does equal the 1/3. Okay. So you do still have to do a third derivative, but I'm not doing it on the crazy stuff. So yeah, it's still a little messy. All right, 5 minute limit of this one. Oh, and if you can't see because it's really light, this is x goes to pi from the left side. We can do the left and right sides. We don't have to do the whole thing. Get your answer yet? What was the first rule I said to do? Right. What's sine of pi? 0. What's cosine of pi? -1, actually. That's the different. That's the thing that makes it. What's 1 minus -1 is 2. It goes up to 0 over 2. You're done. Always try to plug in your number first. For 2 reasons. 1, to see if it works. And 2, you have to show that it's an indeterminate form before you can use the Hospital's rule. So if you don't plug it in, you can't show that it's actually can be done by the Hospital's rule. Okay? So always plug in your number before you go through and try to do all this extra work. Answer 0. We're done. We don't have to do anything for this one. And since it actually goes from both directions to the same thing, it didn't matter from left or right.
Subtract from a negative number plus 1 minus -1. Can you do that?
1 plus 1?
Oh, wait.
Yeah, because 2 negatives make a positive. So yeah, okay. Let me actually write one step prior to this. So I get 1 over 1 minus -1, or sorry, not 1. 0. There we go. Always plug in your numbers first. All right. So let's find this limit. So the question is can I, so if we plug in 0 to this, what happens? So as I'm going from 0 from the right, as I'm coming in, so this is to the right, that matters in this case. The x goes to 0. The ln of x goes to -infinity, right? It's going straight down. So while the way this is set up right here is it doesn't work. Okay. So it's not necessarily when you look at it, it might not pop up, oh, this is an indeterminate form. But whenever you're trying, again, the whole point of the indeterminate forms before was 0 over 0, pi, infinity over infinity equals 1. Those are things that would make sense otherwise. 0 times negative infinity or 0 times infinity would make sense to be 0, but infinity kind of screws this up. So this is an indeterminate form with a product. So the question is now, how can we use L'Hopital's rule when L'Hopital's rule only works with fractions? We need to make this a fraction before we can actually do the work. Okay? So, to do that, we do a nice little trick. So the ln of x will stay there. And I'm going to make that, so I'm going to change my x, okay, to 1 over x. So write this. Is that x?
Yeah.
Yes.
Yeah.
The nice thing about what I just did was I just made it a fraction.
Yeah.
Right? The other way that I could write this would be 1 over x to the negative first power, which honestly I'm going to change this to because that makes it like a little bit easier to do the derivative on. Okay? We now have a fraction. And if I look at 0, it's still going to infinity over, so it's still going to be same concept.
So you just change one of the products.
Yep, to something that's going to make a fraction. Because your goal is just to get it to be a fraction so I can do L'Hopital's rule. Okay, so now let's do my derivatives. So I now have my limit of 1 over x and negative 1 over x squared, which ends up being negative x, which goes to 0. Actually, write the limit in there. Keep change flip. And then we just did with the square root 1 second. Keep that one, and flip that one over. And when you, so you could flip either one over you want. However, flipping over ln of x doesn't make our life easier. Doing the derivative of 1 over ln of x, we have to do the quotient rule for that one. Or the chain rule. And it doesn't really make a nice expression to work with. So you want to use things that are going to make your life easier. And knowing that ln of x, the derivative of it is 1 over x, moving it down, you kind of figure you're going to get some kind of fractions that might be able to cancel each other out. So, but if you try something and it doesn't work, try the other thing. You always can do that. Okay. And the nice thing is when you're looking at limits, you can always graph it to find your answer to verify that you did this correct. Okay? So that's one of those nice things on the test if you're doing it. It's like you can always throw this right into a graph and go, oh, okay, it looks like it's going to 0. That's great. I verified that my answer is correct, so I know I did my work right. If you didn't get something that goes to 0 and you got something else, then it's like, okay, where did I screw up? So you can easily check that work.
Can you show really quick the reciprocals and negative x?
Yeah. So we did 1 over x divided by negative 1 over x squared would be 1 over x times negative x squared over 1, which is negative x. So keep change flow.
So then you would get negative x squared over x.
Yep, which reduces just to negative x because you subtract the exponents. All right. All right, so let's look at these. If we did 1 over, what's ln of 1? 0. So this is getting smaller, correct? So as my denominator gets smaller, my fraction gets what? Bigger, right? So this is going to infinity. If I put 1 in there, that's going to 0. So as it's going from, this is the key, it's going from the right. So as we're getting closer and closer to 0, it's getting smaller and smaller. So again, that's getting to infinity. So I have infinity minus infinity. Again, something that seems like, oh, that would be 0, makes sense, but since it's dealing with infinities, that's also indeterminate. So again, now let's look at how can I take this and change it into something that could work with the L'Hopital's rule. Now, this is a difference. It could also work with sums because you could get infinity and negative infinity, although it very rarely happens. Typically, we get infinity minus infinity. So this typically happens with differences more than sums. If you get infinity plus infinity, it is infinity. So it just goes to infinity. That's not an indeterminate function. So, all right, so we've got 1 over ln of x minus 1 over x minus 1. So we've got two fractions now, right? How can I take those two fractions and make one fraction? How do I take two fractions and make one? Yes. So my common denominator is going to be ln of x and x minus 1. So this is going to be x minus 1, and that's going to be ln of x. So now if I look at this, this actually ends up going to 0 over 0. Because the x minus 1 goes to 0, the ln of x goes to 0. So it basically ends up being 0 over 0, which is an indeterminate form. So therefore, I have to do L'Hopital's rule. So my f of x is x minus 1 minus ln of x. So f prime of x is negative 1 over x. Oh, sorry, 1 minus that. I forgot the 1. 1 minus 1 over x. So my g prime of x, how am I going to find that? Yeah, I got to do the product rule. So the derivative of ln of x is 1 over x times x minus 1 plus ln of x times 1. So I've got where negative 1 over x.
Wait, no, so it's 1 over x times x minus 1
Yes.
equals x minus 1 over x. You cross out both x's and you get negative 1 because the denominator is now 1. So what am I doing now?
Okay, hold on. So this,
Yes.
that's correct, based on what you're saying. Okay. Your issue is over here.
No, I think I just ln x.
So ln of x is ln of x, because remember, product rule is the derivative of the first times the second, plus the first times the derivative of the second. So I didn't do the derivative. You don't have to do the derivative of ln of x again. So the second one was this piece right there was the derivative of that. I am going to clean this up a little bit, but I don't think it's all going to cancel it out. So this becomes x minus 1 over x plus ln of x. Actually, I'm going to do one other thing first. I'll do that next right now. All right, so we've got g of x as cleaned up as I can. Well, so if I put my limit here now, I'm going to have, this is going to 1, the positive side. I have 1 minus 1 over x over x minus 1 over x plus ln of x. That's messy. So if we can make the top and the bottom fractions on their own, we can do the keep, change, flip to try to clean this up so it's just one fraction instead of two fractions, on one fraction on top, one fraction on the bottom, and a mess. So let's look at if we can change f of x. I have 1 minus 1 over x, so my common denominator would be x, so that's just going to be x minus 1. And I can change this one. My common denominator again is going to be x. And I have x minus 1 times ln of x. Oh, no, not times ln of x. That's just x minus 1. Plus x ln of x.
How do you go from what you have in the bottom to what you have now?
This to this?
No, Yeah, all the way at the bottom.
This?
Bottom most
The limit. This piece.
Yes.
That's just that over. Oh, darn it. Caught the edge of my blue box. Hold on. That's just that over that. Because that, remember, when I'm doing L'Hopital's rule, it's the derivative over the derivative. So I just put the derivative over the derivative.
And then how do you get the number you have now? X minus 1 plus X times ln x over x.
Okay, so now it's the same thing I did actually up here. So here I did the common denominator, right? My common denominator was x, correct? Same thing down here. So I took this denominator right there. That's that. That fraction, that part stays there. Now this one I had to multiply by the x, so I have to put an x up on top. So that's where the x on x came from. Yes. You're about to get a little trippier in a second, because watch this. I'm getting rid of the x altogether on the bottom. So since those two are the denominators, if I did keep flip change, they're going to cancel out. And I'm left with just that. Which part?
Everything.
Okay, so you get how I got this common denominator, right? Forget the that. You understand how I got to there?
Yes, you combine.
Okay.
You combine the.
Yes. Right. So the only step I did now to go to from here to here is I did this. I had x minus 1 over x times, and I flipped the second one over.
Wait a second.
Which
No.
cancels those out.
Okay, so my notes are weird. My notes are messed up. I don't know if okay, can you go from the g of x, g prime of x?
Sure.
Can you just go from there?
Yes. Give me a second. I'm going to do it on another slide. I might delete this slide after, but I'm going to do it on this slide.
I get what happened with g of x. Is you going from that common denominator moving on.
All right. So first thing we're going to do before we even do the limit, let's clean up my common denominators. Let's clean these two things up. All right. So we have f prime of x. So that's 1 over 1 minus 1 over x. Common denominator is x. So that's x minus 1. Correct?
Can you answer that a minute?
Yep, sure.
Common denominator because x is also 1.
No, my common it's well, I could put a 1 there, but that doesn't really matter.
Yeah.
Now the same thing in this one. I have x minus 1 over x plus ln of x over 1. My common denominator is still x. So I have x minus 1, and now I got to multiply that one by x. So x times ln of x.
Oh, okay, wait. Why is it? Oh, yeah, over 1. Yeah, okay. That makes sense. that. No, how did you get, okay, now I see what you did. You did the, okay, so what will root of parentheses mean?
That's just the two fractions, the original fractions. That was that and that before I got the common denominator.
Oh, I thought that they helped me to understand what happened there.
I just split it so you can still see the two fractions. This fraction is still x minus 1 over x. That's that. And this one, I had to put an x here and an x there. That's x ln and x over x. So we're cancel x's up, we get back to all of x.
Then this is where you did it keep changing.
My content director, the one who's my boss for the books I'm writing, she is not a math person. She's never taken math, like she's English. That's what her forte is. But she has to go through and edit all the books. So she's like, yep, and I basically learned pre-calculus, now I've learned everything else going through these. She goes, and now I get to learn calculus all next year. And I go, and it's going to be so much easier because you truly know the algebra now.
So how did
Since
you
all the problems are algebra based.
one?
Which one? This one?
Down, there, down.
Okay, so here.
Yeah, now, like kind of like.
Okay, so I'll explain this thing. So it's now, remember, the L'Hopital rules that they're divided by each other. This was is f over g.
Yes.
This is f divided by g. Instead of writing it underneath each other, I wrote it as a division because we're going to flip things.
So this one over.
So this is f of x or f prime of x, and that's g prime of x.
Okay, yeah, you can.
And now I'm going to flip over to g of x, so I have x and flip that over. I can now cancel out my two x's. The one on top and the bottom.
Oh, okay, that's an
And I'm
X,
left
it-
with.
It looks like a one that's been crossed over.
Okay. So that's, I got what you're saying. So that's x minus 1 over x minus 1 plus x ln of x. And no, you cannot cross off the x minus 1s. Because I knew somebody was going to say, can we? No. Remember, you can only cancel things out with multiplication. The bottom is not multiplication. If it was x minus 1 times x ln of x, you could have. But since there's a plus between it, you cannot. All right, so are we good to there?
Oh, no, I just realized. Everything, the new way is denominator is 0, so you have to do it.
Oh yeah, we're not done yet. We are not done yet. I'm going to actually move this over here. And I'm going to erase. Actually, I'm going to erase this whole, I'm actually delete this whole slide because I just basically redid this whole slide. And we're just going to do this piece. So I now have the limit as x goes to 1 from the right side of x minus 1 over x minus 1 plus x ln of x. Now, yes, if you plugged in 1 to this, you still get 0 over 0. So we still have not gotten to a point. So I still have to do the derivatives again. So f prime of x, x minus 1. So f is 1. G prime of x is x minus 1 plus x ln of x equals 1. And then we have to do the product rule on x ln of x. So I have plus ln of x plus x 1 over x. Since somebody's going to ask me if I change that to a 1 real quick. So this is 2 plus ln of x. I'm hoping everybody can get out of x 5. That's 1.
Oh, it's changed.
So x is, nope, we did not do the chain rule, do the product rule. X is 1, negative x is gone, or negative 1 is gone. So now I have to do the chain rule on x ln of x.
Okay,
So it is the derivative of x, which is 1, times the second. That's where that ln of x comes from. And then it's the first, which is the x, times the derivative of the second. Derivative of ln of x is 1 over x. So that's where the x 1 over x comes from. That right there is 1. So I have 1 plus 1 is 2. Yes, always. It's hilarious that as complicated as the stuff's guide and how confused you guide, 1 plus 1 is yes, it's still 2.
Where did 2 come from? I know 1 plus 1 is 2. I'm in knowledge. Oh.
Right there.
Okay. Well, where did the 1 over x go?
X times 1 over x is 1.
Oh, keep it.
No, just it's x over x.
Oh, okay, that's where it came from.
Now we know why all the mistakes that we make are the little stupid ones and not the actual more complicated things. All right, so we've got limit as x goes to 1. We now have 1 over 2 plus ln of x, which is 1/2, and we're done. We're not done for the night, though. We still got one more problem to go. I have one more type of indeterminate function to do. Huh? So the problem is, like, you can graph things, and that's not a horrible way to do it. All right. However, when you're graphing things or when you're using tables, you're estimating. So now, depending on what your application is, an estimation might be fine. But the problem is, how accurate does your estimation have to be to do that? So the nice thing about when you start learning when you can solve things algebraically is you're no longer estimating. You're able to find the exact answer perfectly. And then you can take that and do whatever you want with it. So that's why we look at ways to do it algebraically instead of just the graphic way or things like that. So I know, and you got to realize, like, when I'm doing these examples and stuff, and I'm not picking them actually because the book picked them, but these are ones that I probably would have picked because they're designed to hit certain things that are going to screw you up. Okay? I'm trying to get all the little mistakes that you're going to make here so you can see how they are and so you don't make them later on. All right? So like this one, it's like, okay, we got that extra product rule in there. We have to do common denominators and things like that. That's important to understand and remember how to do, which is stuff that you've done. You just forgot a lot of those little things because you don't do it very often. So that's why these problems are coming up. Okay? So don't freak out. There's reasons for your confusion at these points. I'm not doing this problem. All right, so we will do this problem. Yes, it's a cotangent to the exponent. Because again, remember, we're using things that are going to cause little issues. All right, so these are the first problems that we've looked at that have a power. Okay? So indeterminate powers are ones, again, that make no sense. So, or not necessarily ones that make no sense. Ones that totally make sense but don't actually work the way that they should. Like 0 to the 0. Everything to the 0 power is 1, except 0 to 0. Okay? So it's like that's when I'm like, okay, like, and the same thing, infinity to 0. Infinity doesn't work. 1 to infinity, well, that's still 1. But no, it's not, because again, something just seems wrong about this. So like that's when you're looking at indeterminate. So when you get something that looks to make sense, but has zeros and infinities and things like that in it, that's when you start to look at, okay, is this an indeterminate type? So those are the 3 for the powers. All right, so same things come up. We still need to somehow get a fraction. Okay, because I can't do the L'Hopital's rule in anything except for a fraction. So the question is how do we make this a fraction?
Didn't you say something about the Ellen natural?
Yes, actually, very good. That's actually exactly what we're going to do.
I vaguely remember. I just don't know.
All right, so we're going to make this y equals 1 plus sine to the 4x raised to the cotangent of x. So by doing the ln of both sides, I can bring down the exponent. Okay? So I have ln of y equals cotangent of x, ln of 1 plus sine 4x. That was a horrible way to write 4x. So now I have that. And you're looking at this, goes, wait, we still don't have a fraction. You're right, we don't. But we will in a second. Now I have a fraction.
How did cotangent become?
Ah, let's go tangent.
I know. It was simple. I know it's like.
That's how it became tangent on the bottom.
Oh.
Okay. All right. So we now have this, which is something I can do the L'Hopital's rule on. We just now need to, so we're going to basically, for all intents and purposes, we're going to ignore this piece for right now. Ignore for that second. And we're just going to look at this side. Because we're really finding the limit of both sides. So we're going to find the limit of this side first. So I can do so my f of x is ln of 1 plus sine 4x. I always want to write that as an exponent, and that's not. So f prime of x, and then g of x is tangent of x, and that one's easy. That's just secant squared x. This one, we kind of have to do the chain rule. So the derivative of 1 plus sine 4x is 4 cosine 4x. And the derivative of ln of it is just 1 over whatever was inside, so 1 plus sine 4x. So, that was simple. Everybody got how I got to that? So, when you're doing the chain rule, remember, you do the derivative of the inside. So the derivative of this, the 1 disappears. And you actually have to do the chain rule on sine 4x too. And that's where that 4 comes from. So one of those little things like, I remember talking about like the implied chain rule? That's the implied chain. Whenever you have a function like sine of 4x or cosine of 3x, whatever it happens to be, the number inside will always just come outside, and then it's just, you're doing the derivative of sine or cosine. That's going to come up a ton in Calc when you're looking at integrations, when we're doing integration by parts and stuff like that, that apply. You don't want to have to sit there and write out all your the chain rules for it. It's just one of those things like, just get used to seeing that. So that's where that came from. And then it's just ln of u, which is 1 over u, and that was u. So that's why that came on the bottom of the ln. All right, so we now have the limit, what was it, x goes to 0? Yes. Of ln of y equals the limit as x goes to 0 of 4 cosine 4x over 1 plus sine 4x all over secant squared x. We could keep change flip, but let's just actually plug in 0 and see what we get. So cosine of 0 is 1, so the top's 4. Sine of 0 is 0, so that's 1. And secant of 0 is 0, so that's, secant of 0 is 1, so that's 1. So that just equals 4. Every step you do, always just try to plug in the number quickly to see if it works. Saves you time. So yes, I could have done keep change flip there, brought up the secant squared x. It wouldn't have changed anything. You'd add 4 times 1 over 1, which still is 4. All right, so we've done the limit of this side. We have not done the limit of this side. But that's actually not going to be that overly difficult. So right now I have the limit as x goes to 0 plus of ln of y equals 4. So if I take and change y to be e ln of x, because that would just cancel itself out, right?
So it will be E.
Oh, sorry, not y. Sorry, not x, y. Y is e ln of y. Well, that, because if I cancel out the e and the ln, I'm going to get y, right? Okay, so now I have the limit as x goes to 0 of e ln of y, which equals e to the 4th. So since this is the limit as x goes to something and there's no x here, that is just y equals e to the 4th. We basically got rid of the ln by raising both sides to e. So basically all we did was we did this. We took that and raised that side to the e and that side to the e. That was from the original problem.
Yes.
That was from the other side. That was from here. When I did the limit of this side, that was 4.
So did you just plug in 0 to the top and bottom to get the fractions of 4 over 1 over 1?
Yeah. Yep. You plug in 0 here. Cosine of 0 is 1. So that's 4 times 1 is 4. Sine of 0 is 0, so 1 plus 0 is 1. Secant of 0 is 1. Yep. All right. I have one more crazy one to do. And then we're done. So I'm just going to rewrite this one. All right. So obviously this is 0 to 0 power, right? Okay. So this is where learning how to play around with things comes into play. So I can say x is e ln of x. That's the same thing, correct? Is this true? That's the question. Kind of what I just did with the y, right? Okay, so because the e and the ln cancels out, so that's just x. So I can change this limit to e ln of x to the x power. Correct? Is that true? Okay. Which means this is now the limit as x goes to 0 of e to the x ln of x. Right? Based on the power rules? Awesome. Look back in your notes. What was the answer to that question? What does that limit go to? X ln of x goes to what? We did this problem. That was the product problem, so like 3 or 4 problems ago. There's the problem, right? My limit was 0. Limit as x goes to 0 of x ln of x is 0, correct? Well, that's 0. No, this one right here. This was the x goes to ln of x was 0. That was what we did there. That was that product problem we did. So if we go back to this problem, that is 0. So this goes to e to the 0, which is 1. So the whole concept of proving things is once we've proved something works, I can use it. We already did the work for that. I can use it. So, like, that's another reason why being able to prove things algebraically really helps. Because once we proved it algebraically, we proved it always works for everything. So it's just like when geometry class, when you're sitting there going through the proofs, it was like it made no sense to you, but algebra, when we're going through it, it is a proof. We're just not writing next to it why we did it, but the steps are all proven. So since we did that, and since we've already proven that that equals 0, I can now use it in this problem. So. And we're done for the night.